Hello everyone, welcome to Happy Chemistry. Let's begin today's episode, Error Propagation. Today we will cover the quantitative aspects of the uncertainty as shown in the outline. First, we will talk about relative and percentage uncertainty. These are important in expressing both systematic and random error. There is always an uncertainty associated with the measurements, and to get a more quantitative idea, this uncertainty can be expressed as relative uncertainty and percentage uncertainty. First, we will see what is absolute uncertainty. The absolute uncertainty is the margin of uncertainty associated with a measurement. For example, if the tolerance limit of a burette is plus or minus 0.05 milliliters, then the absolute uncertainty is 0.05 milliliters. What is relative uncertainty? Relative uncertainty is quotient between absolute uncertainty and the magnitude of the measurement. That means relative uncertainty compares the size of the absolute uncertainty with the size of the measurement. Percentage uncertainty is when relative uncertainty is expressed as a percentage. Let's look at an example. We will consider a burette with a tolerance limit plus or minus 0.05 milliliters. A volume of 20 milliliters is measured. Therefore, the delivered volume can vary between 19.05 milliliters to 20.05 milliliters. We will now calculate the relative and percentage uncertainties to represent the associated error in a more quantitative way. To calculate both, we need absolute uncertainty. I mentioned the tolerance limit of the burette is plus or minus 0.05 milliliters. That means the margin of associated uncertainty is 0.05 milliliters. Therefore, the absolute uncertainty is 0.05 milliliters. The magnitude of the measurement is 20 milliliters. The relative uncertainty is calculated by dividing 0.05 milliliters by 20 milliliters, which is 0.0025. Relative uncertainty is converted to percentage, which is 0.25%. These parameters give a more quantitative representation of the error associated with the measurement. Let us now consider how the magnitude of the measurement affects the uncertainty. Consider a burette with tolerance limit plus or minus 0.05 milliliters. That means the absolute uncertainty is 0.05 milliliters. Consider relative and percentage uncertainties for different measurements made. First, 1.00 milliliters is measured. That means the magnitude of the measurement is 1.00 milliliters. Calculated relative uncertainty is 0.05 and calculated percentage uncertainty is 5%. Next, 20.00 milliliters is measured. Calculated relative uncertainty is 0.0025 and calculated percentage uncertainty is 0.25%. Finally, 50.00 milliliters is measured. Calculated relative uncertainty is 0.001 and calculated percentage uncertainty is 0.1%. There is clear trend. For a given absolute uncertainty, larger the measurement, lesser the relative and percentage uncertainty. That means, when selecting the equipment for a measurement, consider the absolute uncertainty and the magnitude of the measurement you are going to make and choose accordingly. As I mentioned in my previous video, there are two types of errors: random error and systematic error. We will first consider random error. Now we will see how to calculate random error. There are two ways random error can be calculated and expressed. First, random error can be expressed as standard deviation of the mean. Let's look at a simple example and see how to calculate mean and the standard deviation. Consider 5 measurements and assume they are 21.50, 20.00, 21.00, 21.75 and 22.00. Here I have shown how to use Microsoft Excel to calculate mean and the standard deviation. The mathematical background will be discussed in a future episode. Mean or average can be calculated in Excel as shown using the function average. Calculated mean is 21.65. Standard deviation can be calculated using the function stdev. Calculated standard deviation is 0.42. Therefore, the associated uncertainty can be expressed 21.65 plus or minus 0.42. Second way of expressing random error is confidence interval. Confidence interval is an estimated range calculated from the measurements to propose plausible values for an unknown parameter. The confidence interval has a confidence level. The true parameter is in the proposed range. The details of the confidence interval will be discussed in a future episode. In most experiments, the arithmetic operations are performed on the numbers obtained from the measurements, which has random errors. Some of them are positive and some of them are negative. Therefore, a simple sum of individual errors will not be the uncertainty of the resultant. Therefore, it is important to study the error propagation during arithmetic functions. We will look at random error propagation during addition and subtraction, multiplication and division, exponents, logarithm and antilogarithm, and natural log and exponential. We will first look at addition and subtraction. In addition and subtraction, resultant absolute uncertainty is calculated. Here, the square of each individual uncertainty is added up and square root is calculated to get the resultant absolute uncertainty. We will see an example. 2.39 with absolute uncertainty 0.02 is added to 1.68 with absolute uncertainty 0.03. The arithmetic answer is 4.07. In the arithmetic part, both numbers have up to 2 decimal places, and the answer is also kept with 2 decimal places. Now we will look at how to calculate the resultant uncertainty. It is calculated according to this equation. Square of 0.02 is added to square of 0.03 and square root is taken. There should be one significant figure in the answer. However, initially it is written as 0.036, where 6, the first insignificant figure, is subscripted. One or more insignificant figures is usually retained to avoid introducing rounding off errors into later calculations through this number. To express it as the final answer, the insignificant figure can be dropped. Therefore, the uncertainty is 0.04. Now we have to consider where the error occurs with respect to the arithmetic answer. The arithmetic answer has 2 decimal points. The error also occurs at the second decimal place. Therefore, final answer can be kept for 2 decimal places, and the final answer is 4.07 plus or minus 0.04. Now we will look at an example for subtraction. 1.16 with absolute uncertainty 0.04 is subtracted from 3.28 with absolute uncertainty 0.05. The arithmetic answer is 2.12. In the arithmetic part, both numbers have up to 2 decimal places, and the answer is also kept with 2 decimal places. Now we will calculate the resultant uncertainty. As in addition, it is calculated using this equation. Square of 0.05 is added to square of 0.04 and square root is taken. There should be one significant figure in the answer. However, initially it is written as 0.064, where 4, the first insignificant figure, is subscripted. To express it as the final answer, the insignificant figure can be dropped and the uncertainty is 0.06. Now we will see where the error occurs with respect to the arithmetic answer. The arithmetic answer has 2 decimal points. The error also occurs at the second decimal place. Therefore, the final answer can be kept for 2 decimal places, and the final answer is 2.12 plus or minus 0.06. Now we will look at multiplication and division. In multiplication and division, resultant percentage uncertainty is calculated. Here, the square of each individual percentage uncertainty is added up and square root is calculated to get the resultant percentage uncertainty. We will see an example for multiplication. 2.39 with absolute uncertainty 0.02 is multiplied by 3.08 with absolute uncertainty 0.02. The arithmetic answer is 7.3612. In arithmetic part, both numbers have 3 significant figures. Therefore, the answer should be kept with 3 significant figures. That means 7.36. Now, we will look at how to calculate the resultant uncertainty. It is calculated according to this equation. Square of percentage uncertainty of 0.02 with respect to 2.39 is added to square of percentage uncertainty of 0.02 with respect to 3.08. And then the square root is taken. There should be one significant figure in the answer. However, initially it is written as 1.1%, where 1 in the decimal place is subscripted to carry out in the calculation as an extra digit. The resultant percentage uncertainty then can be converted to resultant absolute uncertainty with respect to 7.36. The resultant absolute uncertainty is 0.081. The answer should have one significant figure. Therefore, it is written as 1 subscripted to indicate the extra digit. Now we have to consider where the error occurs with respect to the arithmetic answer. The arithmetic answer has 2 decimal points. The error also occurs at the second decimal point. Therefore, final answer can be kept for 2 decimal places, and the final answer is 7.36 plus or minus 0.08. Now we will look at an example for division. 3.28 with absolute uncertainty 0.03 is divided by 1.16 with absolute uncertainty 0.04. The arithmetic answer is 2.82758 and so on. The arithmetic part, both numbers have 3 significant figures. Therefore, the answer should be kept with 3 significant figures. That means the arithmetic answer is 2.83. Now, we will calculate the resultant uncertainty, and it is calculated according to this equation. Square of percentage uncertainty of 0.03 with respect to 3.28 is added to square of percentage uncertainty of 0.04 with respect to 1.16, and then the square root is taken. There should be one significant figure in the answer. It is initially written as 3.6% where 6 in the decimal place is subscripted to carry out in the calculation as an extra digit. The resultant percentage uncertainty is then converted to resultant absolute uncertainty with respect to 2.83. The resultant absolute uncertainty is 0.10. The answer should have one significant figure. Therefore, it is written 0 in the decimal place subscripted to indicate the extra digit carried out during the calculation. Now we have to consider where the error occurs with respect to the arithmetic answer. The arithmetic answer has 2 decimal places. The error occurs at the first decimal place. Therefore, final answer should be kept for 1 decimal place. The correct representation of the final answer is 2.8 plus or minus 0.1. This example leads us to refresh the rule of significant figures when working with the error propagation. The rule is the first digit of the absolute uncertainty is the last significant digit in the answer. Let's look at the same example again. Here, the arithmetic answer should have 3 significant figures. That means it has 2 decimal places. But calculated absolute uncertainty is 0.1. The first digit of absolute uncertainty occurs at the first decimal place. Therefore, the last significant digit in the answer should be the first decimal place. Therefore, the correct representation is 2.8 plus or minus 0.1. I showed detailed calculations for addition and subtraction and multiplication and division. The calculation for other mathematical operations are covered in a similar way. Therefore, now we will look at a summary of random error propagation calculations. To remind the addition and subtraction again, the resultant absolute uncertainty is calculated. This is done by adding up square terms of each individual absolute uncertainty and taking the square root. To remind the multiplication and division, here the resultant percentage uncertainty is calculated. This is done by adding up square terms of each individual percentage uncertainty and taking the square root. The calculated resultant percentage uncertainty is then converted to resultant absolute uncertainty. Next, error propagation in exponents. Here, the resultant percentage uncertainty is calculated. This is done by multiplying the percentage uncertainty of the base by the exponent. The calculated resultant percentage uncertainty can be then converted to resultant absolute uncertainty. Next, error propagation in logarithm. Here, the resultant absolute uncertainty is calculated. This is done by dividing the absolute uncertainty of the argument by the value of the argument and then multiplied by 1 over natural log 10. Next, error propagation in antilogarithm. Here, the resultant absolute uncertainty is calculated. This is done by multiplying the terms natural log 10, absolute uncertainty of the argument, and the value of the solution. Next, error propagation in natural logarithm. Here, the resultant absolute uncertainty is calculated. This is done by dividing the absolute uncertainty of the argument by the value of argument. Next, error propagation in exponential. The exponential e is indicated by non-italic simple letter e, and not to confuse error, which is indicated by italic simple letter e. Here, the resultant absolute uncertainty is calculated. This is done by multiplying the absolute error of the argument by the value of the solution. So, this is a summary of random error propagation calculation when performing all mathematical functions. Now we will look at systematic error propagation. Systematic error propagation is treated differently than random error in arithmetic operations. We will consider two examples for systematic error propagation. First example is rectangular distribution. Rectangular distribution occurs when there is approximately equal probability of finding any value between the known fixed values. For example, x1 and x2 are the known fixed values. Any value can be found between x1 and x2. However, there is negligible probability of finding values outside the fixed range of x1 and x2. The mean of x1 and x2 is x bar. Range on either side of the mean is a. To x1, it is x bar minus a, and to x2, it is x bar plus a. The standard uncertainty of this kind of system is given by x bar plus or minus a divided by square root of 3. An example for this kind of system is uncertainty in atomic and molecular mass due to isotopic variation. The second example is a triangular distribution. Triangular distribution occurs when there is a higher probability of getting the expected fixed value. For example, x1 and x2 are the known fixed values. Any value between x1 and x2 can be obtained. However, there is a higher probability of getting x bar, the mean of x1 and x2. Probability falls off approximately in a linear manner when deviating from the expected fixed value. However, there is negligible probability of finding values outside the fixed range of x1 and x2. The range on either side of the mean is a. To x1, it is x bar minus a, and to x2, it is x bar plus a. The standard uncertainty of this kind of a system is given by x bar plus or minus a divided by square root of 6. Example for this kind of system is uncertainty in multiple deliveries from one pipette due to tolerance limit. So, rectangular distribution and triangular distribution are two examples of how systematic error propagate. In summary, we discussed relative and percentage uncertainty, uncertainty and magnitude of measurement, calculation of random error, that means standard deviation of mean and confidence interval. Propagation of random error. Under this covered all the arithmetic functions. Addition and subtraction, multiplication and division, exponents, logarithm and antilogarithm, natural log and exponential, and rule for significant figures during arithmetic operation. And finally, error propagation and calculation of systematic error. That's the end of today's episode. Hope you liked the video. Give it a big thumbs up. Leave your comments and questions below. Subscribe to my channel. Turn on the notifications to be notified as soon as a new video is uploaded. Do not forget to follow me on Facebook and Instagram. Thank you very much for watching. Stay tuned. See you in my next video. Until then, happy chemistry. Bye bye.